So yeah, I'm Neil Ashton. So I work at Amazon Web Services, but my background was actually as a researcher, coming up with new methods to design planes and cars. I spent some time working in Formula One on the car side, but also at NASA Ames, working on the low boom sort of aircraft, the high lift aircraft, and also I'm a visiting fellow at Oxford, and we were doing quite a lot of work with the DoD on hypersonic turbulence and things like that. But so I'm talking about the theme, I suppose, of computational fluid dynamics. But I thought it might be good to maybe take a step backwards and just see the big picture before diving into some of the details. Because really, I suppose it's all about how do you design the next generation of X, whether it be a hypersonic vehicle, whether it be a rocket, whether it's an autonomous vehicle, like a road vehicle, or an electric vertical and takeoff and landing. There's a huge now change in what is needed to be done to meet the needs of the future, whether it's electric, autonomous, or more sustainable vehicles. But for all of those, companies do need a way of assessing that performance and the efficiency of the new design. And they want to be able to move quickly. As someone said, most companies want to be able to fail fast, see if something works or not, and move to the next thing. So they want to decrease the design cycles because there's a pressure to release things faster. The age of taking 20 to 30 years to design something, I think, is behind us. I think the expectation is to deliver things much faster now. And of course, digital certification is one of the big dreams, whether it's in aerospace, defense, or the automotive. So I thought we'd explore that a little bit further. So I suppose if you do want to design the next generation of something, of course, you could do a physical test, you could go and build it. But for obvious reasons, that has a high expense, both from a pure financial point of view, but also from a time to market point of view. It takes a long time to actually build a model, do all the tests, even though, of course, it is the most accurate thing because it's the real life scenario. But certainly from a vehicle design point of view, talking more from an aerodynamics point of view, that's why we have wind tunnels. Because a wind tunnel allows you to try and represent what's going on, but not actually have to do the complexity of a real flight test. But the problem with the wind tunnels is, of course, one, they're very limited. Of course, this is the famous one at NASA Ames. And as you start to go up the speed range, and certainly once you get into the hypersonic regime, actually wind tunnels become even more complicated and even more difficult to match what's really going on. It's also difficult to actually understand what's going on, as in what is happening with the complexity of the flow around these vehicles, not just is design A better than design B. So of course, that's where the simulation comes in. That's where the computational fluid dynamics comes in, because it means that you don't have to manufacture anything. And of course, you could then theoretically design the vehicle completely digitally before, and then limit the amount of physical testing that needs to be done. The obvious idea for this is that it has a lower cost, but also it's more productive because you can get through more iterations of designs than you could if you had to wait physically to build it. But of course, the big issue is accuracy. And that's the whole point of digital certification, is that the authorities need to have a reassurance that these tools are as accurate as if you were going to be doing the physical test. And of course, without going into too much details, the underpinning of all these is modeling some pretty complicated mathematical equations that people actually developed hundreds of years ago. Now, I wanted to kind of go a little bit deeper again, because this idea of simulation being at a lower cost, but having a challenge with an accuracy, is missing, I suppose, some of the important details. And eventually we'll get through to how this has an impact on high performance computing and how this has an impact on cloud computing. So the first thing to say is that if you're going to do a simulation of next generation fighter aircraft or a hypersonic vehicle or a rocket or even a road vehicle, you could pick the most high fidelity way of simulating it. You could represent all of the complex physics, the turbulent flow that exists around any of the vehicles, and in fact the things that you see probably in front of you now, whether it's a phone or any electronic device has had some sort of fluid dynamics analysis for the cooling, let's say. So you could model it exactly. You could use these CFD approaches, but they come at a cost. And that is exactly why they are still essentially just a research tool. Now, for some of you, these numbers may have a meaning. For others, they may not. So I'll let you look at whatever you want to pick out from this. But the key things is that it is possible. You could do what we call DNS, so it's the highest fidelity of this CFD modeling. But if you do a back of the envelope calculation of a typical type of vehicle, you would probably need about 200,000 cores running for about 90 days. And if you take just an approximate value, just to put a money, financial cost on that, let's say 3 cents per core hour, it'd be about $13 million to do that simulation. So when people say that doing a simulation is a lot cheaper than doing a physical test, you really have to consider, well, what's the cost of your physical test? If it's using a wind tunnel that you already have and you're just 3D printing a part to take in it, you could probably have that wind tunnel for quite a few days for $13 million if you already had the wind tunnel built. So in that case, it would be much cheaper to go and use the wind tunnel, which is absolutely why they still are used. But let's say it's for a very cutting-edge hypersonic vehicle that no wind tunnel can accurately measure, and that if you could do it accurately with CFD, $13 million is actually pretty cheap compared to doing a full flight test. So in that case, it's still worth doing it. But for many people, $13 million for one simulation is probably a bit too much. And you could change the cost of that by up to 50%, and it would still be a lot of money. So the numbers I've used here are orders of magnitude, but hopefully you get the point. But there are approaches that have tried to go, well, how about if we just make it a little bit less accurate, but it gets cheaper to run? And that's another layer of the CFD modeling. The sort of thing that is being done now in limited quantities, but you still need about 40,000 cores running for about 12 days. So this is the sort of stuff that is increasingly being used on some of the big supercomputers around the world. But again, if you work out the maths and work out the cost, you see it's still a lot of money, regardless of whether it's on the cloud or on-prem. Those numbers roughly are the same. But the reason that this simulation is the primary design tool actually for the large majority of aerospace and defense vehicles that you see out there is because they don't use those higher fidelity methods. They in fact use, quote unquote, a lower fidelity model. Again, you don't need to dwell on what we call it, but the point being is that this actually gives the chance to run something in just a couple of hours, maybe using a couple of thousand cores, or a day using just 200 cores, maybe at the cost of just $100. Now you can see why this is so appealing to do simulation, but it's not as accurate. And so that's why still, given that this is the standard in the industry, the simulation is used at the beginning, but then it's not trusted to certify the vehicle or even do the detailed design. Then they have to spend tens or hundreds of millions on flight tests and wind tunnel testing. Now, there is a growing middle ground, and this is more for the people who are into CFD that we're starting to explore, and I'll talk about that a little bit later, but we'll take this as maybe the current potential state of the art. But let's look at a few practical examples. Well, we've been working closely with Boeing and NASA and several other groups on what we call this fourth high-lift prediction workshop. It's essentially a grand challenge to predict the flow of a high-lift aircraft. It's extremely complicated, an aircraft that's at takeoff or landing or operating close to stall conditions, essentially. So it has a relevance to fighter aircraft as well, for example. And what we found through the work that we did, and this is not just AWS and some of the partners, but NASA, Boeing, and others, is that there is a key difference. If you use these lower fidelity methods that maybe only cost you a couple of $100s, they work well when the aircraft is in what we call the sub-stall regime, so it's in standard kind of operating conditions. And that's, by the way, why most of aircraft are designed at cruise using those sort of methods. But once you get to the top, and these graphs are showing you the lift versus an angle of attack. So, as you pitch up, you get more and more lift, but at some point it stalls. Now, clearly, you don't have to be a CFD expert or rocket scientist to know that you don't want the aircraft to stall unless it's doing some sort of maneuver and you have a computer to make it come out of that stall. But with the higher fidelity methods, you can predict much more closely that stall behavior. This essentially means that it's not worth it to use these lower fidelity methods, even if they cost you less, because they can't get a critical part of the design right, which is when is it going to stall? So these high fidelity methods give the chance. And there's actually a physical reason. We have wind tunnel testing where we do what we call the oil flow. So we actually paint the aircraft and you can see where the flow is separating on the aircraft. And then we actually do the same in CFD, and you can see how well it matches. And so the point here, it's not just a number, but it's for the right physical reasons that we can start to get it right. But as you saw, to do this higher fidelity approach, even this middle ground that we spoke about, you still need thousands to tens of thousands of cores to be available. So then you start to come to the question, so you need high performance computing. But as a user of decades of high performance computing, well before I was using the cloud, this is a common pain point of people being stuck in a queue and then asking some sort of sysadmin, can I please bump up my priority? And this constant challenge of managing capacity and resources. Or running out of disk space, and as the person before just gave the example, you've got your data for 30 days and then you've got to get rid of it. As an interesting data point, we have individual customers, so I won't name who they are, but there are customers on AWS who just by themselves have more than an exabyte of data. So there's a lot of data space out there that you can fill. And I suppose the way that you see it is that there is two different types of models that, on the left, I suppose you have a fixed size, where if you have a designer who wants to do that high fidelity run of that vehicle, the problem is how do they fit that job, that game of Tetris, into their existing fixed capacity system that they procured. Of course, the cloud model is that you can actually scale out because, of course, our systems are at extreme scale. So you can fit inside that much more easily. And of course, there's also the advantage of the pay-as-you-go model. But I'll address that point a bit later because I think someone brought it up in the discussion, which was very interesting. Now, this actually matters from a global point of view because actually most of the companies that we speak to, even if they're mainly, let's say, doing work in the US, nowadays there tends to be a lot more of a global presence. That, there are teams that may be based out on the East Coast of the US, but they also have engineers, in London, or they have a development team in Mumbai. And so they want to be able to give those same quality of resources all around the world, wherever they need to be. And that's obviously a clear advantage when you have a more global, infrastructure. Of course, there's also the benefit of being able to have different region types. So we have the commercial regions, but also things like GovCloud for ITAR workloads. But one interesting data point, because I was actually giving a talk yesterday with the person from ARM being the chip designer. They actually run on AWS, and the interesting data point, they run on average 63 million jobs a week on AWS. On average, about 10 million jobs a day. It takes 33 minutes is the average runtime. and they use up to about 350,000 vCPUs. And you can see from these graphs, oh, and by the way, this is all on spot, so this is all spare capacity, just as an interesting data point. But from a security point of view, obviously one of the things, particularly for the industry that most of you are in, is the need to work at different levels of classification. So obviously with AWS, there is secret regions for classified, secret, and top secret. And actually there are, widely used CFD codes from NASA and US governments like Overflow and Fun3D, running on tens of thousands of cores, every day. Now, for some of you, this may mean something, and unfortunately, I can't actually see the audience. So if any of you are falling asleep, then I would have got the hint more easily if I was there. But for one of the big questions that you hear from high performance computing is this idea of, if you go into the cloud, you're using a virtual machine, surely you pay some sort of penalty essentially for that. Well, with AWS, there's been a huge innovation on the hypervisor system. And without dwelling on that too much, the point is, if you take 4 HPC codes, actually these are not just CFD, this is CFD, a genomics, a weather code, as well as a standard benchmark. The difference between running on a bare metal versus with a hypervisor is less than 0.5%. So actually, you get all the benefit of the virtual machines, and the performance is essentially, the same as a bare metal. And that's thanks to the Nitro system. It's basically offload it onto another card. So rather than traditional hypervisor where you have to lose some of the cores and memory, it's actually on a separate chip. And just an example of this, and again, this will mean something to some and less to others. We took a benchmark of a typical type of CFD code, took a problem, it's actually a Formula One car, but it gives basically the same analogy if it was a plane or a rocket, as long as the flow was roughly the same. And you can see that scaling is actually as good. This was a public available data for Cray XC50. So you still get great performance running out, onto thousands of cores. It's true that probably 10 years ago, this wouldn't have been true, but there's been huge innovations now in high performance computing in the cloud to enable this sort of thing. And again, the scale, and I don't show these numbers just as, show big numbers for the sake of big numbers. I'm showing these numbers because it links to that idea of high fidelity CFD. If you really want to do digital certification, you need to run big models because you need the accuracy. And if you're going to run a big model, you need to run it on lots of cores. And that's exactly what this is about. Now, I'll quickly touch on the GPU because one of the big growing areas now is all those numbers I showed at the beginning in terms of time and cost were based on CPUs. But you can get a huge advantage. And actually, many of the NASA codes like Fun3D have actually moved and are porting to GPUs just because you can see such a great speed up. This graph shows some work we did where the red is the GPU. Essentially, you get 3 or 4 times the speed up compared to CPUs, even as you scale it out to as big as it can go, essentially. So it's a fair comparison. But what most people don't realize is that actually the GPUs are cheaper because you don't need as many of them because they pack so much compute. So all those numbers that I gave at the beginning of saying, oh, it's $100 per CFD or 10,000, you can actually cut them by 2 or 3 times by moving to GPUs. This has often not been so clear because I guess with an on-premise system, it's harder to pull out the costs. With a cloud, we show you what the costs are, and so you can much more easily compare against different things. So GPUs clearly make a difference. One thing I would say, just in terms of more the DevOps kind of framework, is the key difference here is if you want to change your environment, and so the person was just saying then, you want compute, but you sometimes want disk. Well, if you want to set up a cluster that has a multi-petabyte file system underneath it, you can just specify that in the code that creates the cluster. Hey, I want this to be attached. It's going to be this size. And then if you want to update it and say, now I need it all based on GPUs, you just change the line of code and then it updates the cluster in like 10 minutes and you've got access now to a GPU cluster. So it's a lot more flexible for people to be able to use. Now, of course, the cost one is probably the one that, as you were saying, can sometimes be the most difficult to adjust to, because I suppose you're used to having had a capital cost which has already been spent, and so now the end user, in a sense, has no concept of cost because the system's already been bought. Now, companies are adapting to that by having, using a lot of our services to track budgets and spending. You can tag every single thing if you want to. Of course, that is also a learning ramp to get used to that. But it is possible also to use what's called reserved instances and savings plans, which is the same model as on-prem. You just say, I want 10 nodes. I'm going to pay for 1 or 3 years use of it, and I will fix my cluster to that size. So I know what I've spent because I've literally just bought it. It's a fixed, I can even pay for it completely up front. But the advantage is you could also burst on top of it. So you can obviously have the pay as you go, but you can also have a bit more static costs by just paying up front for a fixed amount of resources as well. So I suppose one final few examples like Joby, that some of you may or may not know, really exciting startup building the eVTOL to try and fix the urban air challenge of getting across New York or London or any of the big cities at rush hours. And they were a startup running actually in GovCloud as well because of the codes that they're using. And they wanted to design this vehicle. And the great thing is that they could just spin it up. They didn't have to worry about stuff. But also they kept all their data. So they have hundreds of terabytes of data stored in S3 just in case they ever needed again. Same with Boom Supersonic, doing the low, quieter version of Concorde, of course, or equivalent to Concorde. And they've got over 500 terabytes of data stored in S3. And I wouldn't say that they're a particularly big data example, but it's still a use case. The final thing that I think is personally interesting is the link with machine learning. So everything I talked about is in some ways traditional HPC. But now the majority, whether you're in defense or aerospace or automotive or manufacturing, is how can we use machine learning to either extract relationships from that simulation data, to accelerate the simulations by embedding some sort of machine learning inside of it, or learn the solutions themselves. And apologies, my dog's barking probably at some Amazon delivery going on now. And this is one of the things, see, if I was there in person, I wouldn't have a dog barking with her. So we try to do this with Formula One. I'll make it quick. We trained a deep learning model to learn between the input and the output. And that's exactly what we enabled them to do. So essentially they could replicate what an engineer was doing by having this deep learning learn what they were inputting and what they were getting out. And now they can replicate it by just doing an inference in a few seconds. So hopefully that wasn't too much. I never know with CFD and HPC how deep to go. So that's why I tried to start a little bit higher. But I suppose the idea is if you want to be doing this data-driven design process and digital certification, you can be using these simulation approaches, but you need to go to higher fidelity methods. If you're going to go to higher fidelity, you need high performance computing, but you need a lot of it. And if you want to give people access to it, then the cloud gives you that ability. And of course, I didn't talk about the hot topic of digital twins, but there's a logical link to that. So with that, thank you very much. And if there's any time for questions, happy to take them.
Thank you very much.